Okay, let's dive into this explainer. Have you ever really looked at a map and wondered how all those tiny lines, colors, and shapes somehow manage to capture our entire massive planet on a single piece of paper? Well, today we're going to entirely demystify the language of maps. But honestly, we're not just stopping at learning how to read them. We're going to use those newfound skills to uncover the absolutely epic, constantly moving history of the Earth itself. We're taking a journey from the bare bones basics of cartography all the way back to a time when our planet looked completely, literally unrecognizable. Here is our roadmap for today. We'll start with the 5 map elements, then look at finding direction and scale, and move on to legends, symbols, and grids. After we've got the basics down, things get wild with the continental drift theory. And finally, the breakup of Pangaea. Let's just jump right in. Section 1, the 5 map elements, also known as the cartographer's toolkit. So, to read a map accurately, you really need a decoder ring, right? And every single map, no matter how simple or incredibly complex it is, relies on 5 essential components. First up, the map title. This just tells you what you're actually looking at, like, say, the political borders of a country. Second is direction, which orients you so you actually know which way is up. Third is scale, and this is absolutely crucial. It lets you calculate real-world distances based on what's on the paper. Fourth is the legend or key, which translates all the symbols and colors for you. And finally, the grid system. Those are the intersecting horizontal and vertical lines that help you pinpoint an exact location. Grasping these 5 elements, that's your foundation for navigating literally any map in the world. Moving on to Section 2, finding direction and scale, or how we shrink the world. Now let's explore how we actually orient ourselves. You've probably seen a compass rose before, and it brilliantly illustrates the whole concept of direction. You definitely know the 4 main cardinal directions, right? North, south, east, and west. On most maps, north is that arrow pointing straight to the top. But for true real-world precision, cartographers have to subdivide these into intermediate directions. Places sitting halfway between north and east are, you guessed it, northeast. And you can chop those up even further into north-northeast and so on. That 360-degree precision is a total game changer. And it's essential whether you're hiking a remote trail or, piloting a giant cargo ship. Okay, once you know your direction, you gotta know how far you're actually going. Think of the map scale as a magical shrink ray that basically comes in 3 different settings. First is the verbal scale. This is super straightforward. It just tells you in words that, for example, 1 centimeter on the map equals 5 kilometers on the ground. Next up is the graphical or linear scale. This is usually that little drawn line at the bottom of the map, chopped up into lengths that represent physical distances. And lastly, we have the representative fraction, or RF. This one is a mathematical ratio, like 1 to 50,000. It just means 1 unit of measurement on the map, let's say an inch or centimeter, represents exactly 50,000 of those exact same units out in the real world. Which brings us to Section 3, legends, symbols, and grids. Time to translate the map. Every map needs a translation dictionary. And what's honestly so amazing about cartography is that it acts as a global language. These colorful little symbols and signs are recognized internationally by convention. Universally accepted colors act as a quick visual shorthand. For instance, blue for perennial water bodies, brown for mountains and hills, and green for natural vegetation. It's awesome because whether you speak the local language or not, if you see a blue meandering line on a piece of paper, you instantly know you're looking at a river. So all of this builds into the grid system, which is basically the Earth's ultimate address book. It's built out of 2 sets of intersecting lines. First, you have latitudes. These are the horizontal east-west lines. The granddaddy of them all is the equator at 0 degrees, completely dividing the Earth into the northern and southern hemispheres. They form full circles that actually get smaller the closer you get to the poles. On the flip side, we have longitudes. These are the vertical north-south lines running from pole to pole as semicircles. The starting point here is the prime meridian, passing right through Greenwich, London at 0 degrees. If you want to locate any specific city on the globe, you just find the exact intersection of its horizontal latitude and vertical longitude. Boom, you're there. All right, so we've mastered navigating our present-day map. We get the grid, the scale, the legend. We're cartographers now. But we really need to pause for a second and ask a completely mind-bending question about the very ground we're standing on right now. Has the map of the world always looked like this? Let's dig into that in Section 4, the continental drift theory, the mystery of the moving continents. To actually answer that question, we're going to have to time travel back to 1912 and meet a German meteorologist named Alfred Wegener. Now, Wegener looked at the familiar 7 continents we know today, but he proposed something completely radical. He suggested that millions of years ago they were all mashed together into one giant continuous landmass. He named this massive supercontinent Pangaea, and surrounding this colossal block of Earth was just a single global ocean called Panthalassa. This wild idea became known as the continental drift theory. I mean, imagine looking at a giant planetary jigsaw puzzle. People had honestly noticed for a while that the coastlines of certain continents kind of looked like they could match up. But Wegener actually used cold, hard facts from biology and geology to back it up. He pointed out the frankly uncanny jigsaw fit of the east coast of South America slotting right into the west coast of Africa. He argued that, hey, they didn't just look like puzzle pieces, they actually were puzzle pieces that had just slowly drifted apart over immense stretches of time. So let's look at how that happened in Section 5, the breakup of Pangaea. Get ready for a deep time journey. Okay, let's put our map reading skills to the test and chart a timeline of how the Earth's surface evolved over hundreds of millions of years. Because of the work of cartographers, we can trace this physical evolution step by step. We start way back in the Permian period, roughly 225 million years ago, when Pangaea was totally intact. Then, fast forward to the Triassic period, 200 million years ago. That's when the first major cracks start showing up. By the Jurassic period, 150 million years ago, you can see these vast separations, which leads us all the way to the very recognizable fragmentation of the Cretaceous period, about 65 million years ago. Fun fact, that's right around the time the dinosaurs were facing extinction. It's really incredible to watch this progression unfold. Around 200 million years ago, that single supercontinent, Pangaea, first splits into 2 major landmasses. You have Laurasia up in the north and Gondwanaland down in the south, and they're separated by this new body of water called the Tethys Sea. Over the next millions of years, through the Jurassic and Cretaceous periods, these absolutely enormous chunks of land just kept fracturing. They slowly crept across the globe, eventually arriving in the exact positions we recognize on our world map today. You know, I think the most fascinating takeaway from this entire explainer is the realization that maps, they're really just snapshots in time. The very ground beneath our feet is completely dynamic. The continents are still drifting today, literally at about the same speed your fingernails grow. Our current map is just a temporary arrangement, which leaves us with a pretty incredible thought to chew on. How are future cartographers going to draw the Earth 100 million years from today? Next time you look at a world map, just remember, you aren't only looking at geography. You are looking at a single frame in the longest, slowest movie ever made. Thanks so much for diving into this with me.